Welcome back. This is EasySpin Academy 2020, day number 2, and we are now in the Q&A session at the end of our day. One reminder that after the Q&A session, please head over to gather.town. The link is provided on the Academy website, where we have our happy hour. Me and some other EasySpin folks will be there, and if your question hasn't been answered yet on Slido or in this Q&A session, please track us down in the happy hour, and we're happy to discuss any other questions you have. If you have feature requests, come there, or if you have complaints, also let us know. We're happy to chat. Okay, so I looked a little bit through Slido and picked out some of the questions which I think I can answer reasonably well here in a general Q&A session. So let's go back to MATLAB. The most upvoted question on Slido was about what the option .llmk actually means and how that works for Chile. So let me briefly explain. In Chile, the opt llmk specifies the basis set being used, and there's 4 numbers to that. We can start with all zeros. What do those mean? The first one is the odd L max to include. The second one is the even L max. The third one is the M max, and the last one is the K max. So what you need to understand is that basically Chile models the orientational distribution using some orientational basis functions, which are called Wigner functions. These are kind of very similar to spherical harmonics, which depend only on 2 angles, but Wigner functions depend on 3 angles, right? And as a consequence, they also depend on 3 parameters, on L, M, and K. So a typical Wigner function depends on L, M, and K, and L can be any value starting from 0, 1, 2, 3, and so on. M can be 0, or it can be plus minus 1, and all the way up to plus minus L. And the same applies for K. K is similar. Let's write it out. 0, plus minus 1, all the way up to plus minus L. Now, ideally, a perfect basis would have an infinite L and all possible M's and K's for all those L's. It would be infinitely large. Luckily, we don't need that because the orientational dependence is pretty smooth. So we can limit ourselves to smaller L values and also to smaller M and K values as given by the L. Now there's a special thing about L that very often in typical cases actually I've swapped those around. The first one is the even L max. The second one is the odd L max. That the even functions and the odd functions have different importance, and very often the odd L functions don't contribute a lot. So having these 2 separate allows you just to include even L's and exclude all the odd L's. Okay. So this is basically how it works. And if you increase all these 4 numbers successively, you include more and more basis functions, and you can model the orientational distribution much more accurately. And so in the limit, the higher these values are, the better your model is. Okay, and there's just no general recipe, unfortunately, of how to predict for a given nitroxide spectrum with a given correlation time and a given orientational potential what the minimally required basis size is to make the spectrum really smooth. So you really have to experiment with this. In the old EasySpin version 5.2, this was an optional input, but in the new version, we're making this a required input because experience has shown that people tend not to check this and then simulate spectra that have basis sizes that are too small, giving inaccurate spectra. So this will probably be, we might rename this for the final 6.0 release, will be a required parameter. Okay, so this is what LLMK means. The larger these numbers are, the more orientational basis functions are included. Now, these orientational basis functions are also useful, and this is going to address the second question, what cis potential is for Chile simulations. This is again all talking about Chile. So cis.potential specifies an ordering potential as a function of angles in terms of an energy, right? So potential is an energy. And the three numbers, there's four numbers here, an L, an M, and a K, and some value, let's call it lambda, okay? So L and K are again the three indices needed to specify a particular orientational function, and lambda is the linear combination coefficient for that particular function. And using these, you can put together a more complex ordering potential. Let's do a very simple exploration here. Let's start out with a 0, 0, 0 function, right? A 0, 0, 0 function, you can put any lambda in there, is fully spherically symmetric. We can look at this with Ori potential plot and just feed in the sys dot potential. All right, if you run this, you can see, let's go over the populations. You see it's white everywhere, indicating it's the same energy everywhere and the same populations. Okay, now let's change the L to 2. So the L is 2, M is 0, K is 0. And let's maybe use a little larger lambda. This lambda is a multiple of KT, multiple of KB times T, which is the thermal energy. So Boltzmann constant times temperature. And lambda is just a multiple of that. So if lambda is 2, it means that the energy for this function is 2 times the thermal energy. Okay, let's make it 2.5. All right, and now you can see what we've already seen before, that now we have lots of populations at the North and South Pole and very little population along the equator. If I change the sign of lambda for this particular function, we're going to invert the energy landscape and therefore also invert where the nitroxides hang out, right? And so if you look now, you can see there is very little population along the z-axis and a lot of population around the equator. Okay. Now we can also look at more complicated functions like 4, 3, 2. All right? This is just a single function. And now you can see that this is now more an oscillatory function. Why is this zooming? It should be rotating. Okay. Now you can see this has way more structure to it. And again, there is minima where the nitroxides congregate, and there's maxima where they don't hang out in terms of orientation. You know, these are functions of 3 angles, but we're only plotting 2 of them. And if you look here on top in the title, it does say the equation population is only for alpha, beta, and 0. But you can swap this around by clicking this button here at the bottom that plots the beta gamma dependence of this function. It's a function of 3 Euler angles, alpha, beta, and gamma. If you want to add more than one of these functions to your potential, to your orientation potential, you just do a semicolon and add another function. So we can add a 2, 0, 0 function with 1.5, maybe this one we just also make 1.2. So now we would have the 4, 3, 2 function with an energy of 1.2 kT and a 2, 0, 0 function with an energy of 1.5 kT. And let's look at this. And now you can see a combination. You can see kind of a combination of the two. And this can get arbitrarily complex. And if you have some orientational potentials from your molecular dynamics simulations, you could even least squares fit these numbers to the evidence you have from molecular dynamics. So I hope that explains a little bit how what these LMK numbers mean. These are Wigner functions. And in fact, there's a whole other section of EasySpin that can actually give you direct access to calculating these Wigner functions. But just remember Ori potential plot. It's super useful. But it's also, again, it's new in EasySpin 6. It's not available in EasySpin 5.2. Another question was about garlic versus chili. And garlic and chili can both be used in the same fast motion regime. And the question was, when does garlic break down? So garlic makes a perturbation approximation. And how can you figure out when it breaks down? Well, the only way is you just need to run the full chili simulation using the exact theory. And this is the same as for pepper, where we have multiple levels of theory. The highest level of theory, which is unfortunately the slowest, is the reference point. And there is no general recipe that tells us when some approximation breaks down or not. Because spin systems vary by so many things that in their parameters. It's impossible to give a general recipe. So in these cases, run garlic with your correlation, rotational correlation time. Run chili with the same data and compare them. And if they match, then it means you can use garlic. But if they don't, you have to use chili, which is the more complete theory. So that is all about chili and chili versus garlic. There were a ton of questions about fitting. Let's see if I can answer them all. So one of them was about, can you fit pulse CPR data? And the answer is yes. You can either use Saffron directly, and you can fit time domain echo modulation, or if you do some post-processing on your time domain pulse CPR data and you want to actually fit the spectrum itself, for example, an ECM or an Endor spectrum, then you can write a custom fit function. And yeah, so it's just straightforward. You can use saffron the same way, use pepper or chili or garlic for ESFit. You could even write your own EasySpin style simulation function and then use that as with ESFit. So the only requirement for these simulations function is that they take 3 inputs, sys, exp, opt. It doesn't matter what's in those inputs as long as you can make use of them within your simulation function and you return a simulated data vector. And if you write this custom function, you could equally well, fit, let's say, a binding curve of a protein substrate equilibrium. It's totally possible. It doesn't even have to do with EPR. Using this custom function approach is extremely flexible. Use this custom function also to fit multiple spectra. So the way to do that is, let's say you have, you have 2 different spectra. Maybe you have an X band and a W band spectrum of the same sample, right? And you want to fit them simultaneously in a global way. Let's say you have the X band spectrum and you have the W band spectrum loaded. What you need to do is combine those data into a single vector, just kind of concatenate the X band and the W band spectrum, and then feed this into ESFit with your own sim function and so on here. Probably sys and then exp and opt. And now you have to write your own function, simulation function, that returns the same type of data, which means an X band spectrum attached to a W band spectrum. So let's do it quickly. My sim fun, it just takes sys, exp and opt. And what you can do now, you can simulate your X band spectrum. Let's call it simulated X band spectrum using pepper. Let's say sys, and then you have to ask an exp x thing here. And you might want to explicitly specify your fields. Exp dot microwave frequency here 9.5. And then you do the same for the W band spectrum that you want to simulate. Let's say that's at 93 gigahertz, and you simulate that, and at the end you calculate this, you concatenate those two together, spec X sim and then spec W sim, right? And that's it, that's what's being returned. So you're basically constructing a concatenation of all the spectra that you want to fit. This is how it works currently, both in 5.2 and in 6.0. But we do have some changes planned to make this a little easier to do these types of multispectral fits. So stay tuned. If you're using 6.0, be ready for some changes in the near future. If you like the current interface, you can equally well stay with 5.2 until the 6.0 version has settled into its final set of features. But we would really appreciate if you guys keep using 6.0 and give us feedback on what we can improve as it evolves in the next couple of months. So that is how you can fit multiple spectra at the same time. So it's really powerful to use these custom simulation functions. Another question was about function handles. So in the past, in EasySpin 5.2, It was also possible, let's say, write this out, EasySpin 5.2. It's possible to say ESFit and then give a string for the name of the function, data and so on. Sysexopt, sysvary xopt. I think I had that wrong here as well. This is no longer possible because we're EasySpin 6 is now taking full advantage of these function handles, which allow a much greater variety of algorithms to run. It's much easier to ship them around internally, and it's kind of the mechanics that's necessary for us to make global fitting or multispectral fitting much easier for you. So from now on, this will actually create an error. An ESFit will crash, and you just basically have to replace it by the function handle at Pepper. And I really recommend you to look up in the MATLAB help, which you can access here on the top right. And then look for function handles in the documentation. It is a strange concept if you haven't encountered it before, but it has very powerful implications of what you can do. So function handles. In MATLAB, calls them variables that allow you to invoke a function indirectly, right? And so you can actually look for how to create them, how to pass them around, and so on. This is well documented in MATLAB. We will see function handles appear more and more in EasySpin 6.0 because they're just so nice. So for example, if you want to specify your own orientational distribution, you're not happy with this type of interface of sys.potential, you could, our plan is to allow it for you to just pass a function handle that EasySpin will just call and then expect you to return an orientation weight. Let's say it will call it with certain angles and the function then returns a weight. So this way it will make it more flexible for you to use. So expect function handles to appear more and more. It's worthwhile to get acquainted with them. Another ESFit question was about whether it's possible to exclude regions, right? Sometimes you have a spectrum and maybe you have an artifact or a background signal which you just don't want to include in your fitting. In EasySpin 5.2 and in the current 6.0 development version, there is no simple way of excluding it with just a simple mask or a region selector, but this is planned. But meanwhile, you can actually work around that. Again, using custom functions. What you can do, you can write a custom function that just clips out that part of the spectrum. Let's say the center third of your spectrum is a background. So what you do, you load your data and then clip out the central third, just cut it out and just make the spectrum, just attach the two remaining thirds together. And then in your custom simulation function, just simulate the spectrum with a full field range, then also clip out the center and attach them together. And this way you have kind of manually excised the regions that you're not interested in. It's a little bit of a kind of kludge, right? It's a bit hacky, but it works. The final EasySpin 6 release will actually have a nice selector mask where you specify which parts of the spectrum the least squares fitter should ignore and which ones should be taken into account. Another really good question for ESFit for fitting is about parameter uncertainties. Is ESFit able to calculate the errors in the fitted parameters? Answer is no for 5.2 and not yet for 6.0. This is in the works. We actually already have a working version that calculates uncertainties based on the Jacobian approach. And it will appear fairly soon in the next development release of 6.0. So you can look forward. There will be probably a separate button which you click, and then we'll do a few more simulations to calculate some gradients, and from those gradients then derive the fitting errors, which you can then report in your publications. So stay tuned. It is really just around the corner. And there's one more questions about ESFit that I was able that I picked out. Somebody asked, what target function should one typically use, and what are the advantages of just fitting the spectrum as is versus the integral of the spectrum versus the double integral or versus the Fourier transform? So changing these fitting targets changes the shape of the error surface. It doesn't move the global minimum around. If you have a fit, it's going to be a fit no matter what you look at the spectrum itself or at the integral of the spectrum, right? But some of the side minima are going to be eliminated. For example, let's say you have a spectrum with 4 peaks, let's say from a copper single crystal, right? And so let's say that my bottom hand is the experimental spectrum and the top hand is the simulated spectrum, right? If you, for example, you get in a situation where the G values are not right and you fit 2 of the 4 lines like this, you're in a local minimum, because moving with my top simulation hand to the left or to the right will just increase the error, right? And so the simulation algorithm really gets stuck here, will never get out. And the same if you fit 3 of the 4 peaks, it's again stuck. So when you have many lines, you have many minima. And it's really hard to get out of these minima. But if you generate the double integral or the integral of this, you can reduce the number of minima. I think this is actually worthwhile showing quickly, and maybe this is the last thing we do in this general Q&A session. Let's take a spin system with a G equals of 2. Let's use a copper 63 nucleus, and let's put some hyperfine coupling in there. Okay, and now plot, just choose an experiment, an X-band experiment, and just calculate the spectrum using Pepper. Maybe add a little bit of broadening, line at peak to peak broadening, and then plot the spectrum. Okay, if you run this, I think we should clear the figure. Okay, this doesn't like this function. There's the description here. Let's move over to a new folder here, a file here. Okay, so it's a little too narrow, or a little too wide. Let's narrow it down. Let's take this example and extend the range a little bit to 330 and 348 nanometer millitesla. Okay, so this is now the spectrum as measured. Now we can look at the double integral. For this, we're just going to plot the cumulative sum of the cumulative sum of the spectrum. And this is how the double integral looks like, right? It's kind of what you know from NMR. That's how you quantitate spins, right? So now there's no more local minima, right? Because if this curve is off, if your simulation is off with its G value, it's not going to fit anywhere because you're going steps up. So by using these other target functions, you can massage the error surface to have fewer local minima. And it usually works well for spectra with many peaks. Okay. So I think that is some of the important questions, or some of the ones I was able to pick out. I'm sorry I'm not able to answer everybody's question here, but I think most questions got some answer on Slido. And if you have more questions and want to discuss more, please come over to the happy hour on gather.town, where we can discuss more. I will be there starting in about 6 minutes, and then from 2 hours from there. This concludes the question and answer sessions of today, and this is also the official end of day 2 of the EasySpin Academy sessions. We just have the happy hour left. For tomorrow, we'll again have 6 sessions, and the first 3 sessions have topics that are planned out. We'll have an overview of other tools that EasySpin enables on top of just the simulation functions. We'll talk about Endor, and we talk about shape pulses. And after that, we'll talk about the topics that will glean from the Slido poll that I really urge you to fill out. Okay? So with this, have a good night or good afternoon. See you over at the happy hour or tomorrow at day 3 for the EasySpin Academy 2020. Bye-bye.